we're doing any kind of math calculations. So you might see in a dosage calculation, you might end up having something like a doctor's orders where the doctor says, okay, I want you to give 0.25 milligrams of digoxin. Digoxin is a heart medication. It helps to slow and steady heart rate, commonly give after a person has a heart attack. So if they order 0.25 milligrams of digoxin, that's the amount. So that's the mass, right? So milligrams would be, this is the mass of the medicine. You have a solution. So anything that is a solution means it's a liquid form. Okay, so instead of being in a pill, this is a solution. So that means that, like if you've ever had, if you make a solution of anything, you put some amount of something into a liquid component, typically water. So this is a solution of 500 micrograms per milliliter. So a solution, you know that this is a liquid mixture. That means that I have medicine in some kind of volume, typically of water. Right, so they add the medicine, like if you've ever given your kid amoxicillin or you've ever had amoxicillin, the pink liquid when you were a kid, that comes to the pharmacy is a powder. The pharmacist adds water to it and shakes it and shakes it and shakes it to make the suspension. And so that's why every time you take it out of the refrigerator, you shake it before you dispense it. So that is a solution. It's really a suspension. It settles out. But if you're given that, that's what you're looking at. If you see like micrograms or milligrams or something per mil, then you know that this is some amount in a liquid volume. So if I want to know what volume, the volume I want to figure out is I want to figure out milliliters. So if I can figure out how to multiply and get my units to cancel, just like a unit conversion, I'm really going to use that solution as a unit conversion to be able to cancel the mass amounts and figure out milliliters. But just like I said, you can't multiply 12 inches times 3 feet. You have to convert the 12 inches to feet, or you have to convert the 3 feet to inches. You can't multiply unless the units are the same. So notice I've got milligrams and I got micrograms. You're going to have to convert one of them. And it really doesn't matter. The answer won't be different. You can convert one or the other. I personally would convert milligrams to micrograms because it's all by itself. So it's not part of a solution concentration. So I've got to make milligrams and micrograms have the same unit value. So the first step I would do, the first step that I would do, it's because I'm left-handed and my little controls are down in the bottom left-hand corner. Because everything is built for right-handed people. And I actually messaged Microsoft and they were like, well, we're not changing that. I was like, thanks. That was very helpful. So that's why I have this that jumps around all the time. So I'm going to convert 0.25 milligrams of this medicine. I want to know what it is in micrograms. Because once I get it in micrograms, I can set it up and have my units cancel and figure out milliliters of the medicine that I would give. So is this a one-step or a two-step? Two, because you see milligrams and micrograms. So what are you going to go to first? 2 grams, right? So remember, if you see 2 prefixes, if the given unit and desired unit both have prefixes, just go to the base unit in between. And that way, you only have to remember what those prefixes mean relative to the base unit. So in the first step, what unit goes on the bottom? Milligrams, what goes on top? Milli gets 1,000. Grams gets the 1, right? So anytime you have milli, 1,000 goes in front of the milli. Base unit gets the 1. So that's the first step. So I'm going to get rid of grams. I'm setting it up so they cancel. So second step, I've got to do the second arrow. So what goes on the bottom this time? Grams. And on top, the mu, the microgram. What goes in front of the mu? A million. And grams gets a 1. Okay, so in doing this math, 0.25 times 1 does nothing, but times a million does change it. Okay, so 0.25 times a million, then divide it by 1,000. It's 250. And now make sure that you put the answered unit there. So now I know I have 250 micrograms. Right, so remember, like, just practice. There's those practice sheets that I gave you with unit conversions. Just kind of like trying to get yourself kind of in this mindset. Just set it up. Notice in this, I always say, like, you follow the units. So the units can really help make sure that you always put it correct so that you don't accidentally divide by 1,000 instead of multiply by 1,000. So if you keep the units, not just the numbers, you can be sure that the answer you're coming up with is going to be true. And sometimes this can be really important if you're going back and checking medication dosages so that you don't end up trying to give somebody 1,000,000 times more than you actually should because you multiplied instead of, that gets awkward really fast, okay? So if I've got this much medicine, so now if I have 250 micrograms of this medicine, how can I use the concentration of the solution to figure out the milliliters? What unit could I put on the bottom? If I put, not milligrams, if I put micrograms on the bottom and milliliters on the top, so I'm just taking the concentration, what goes in front of the micrograms from that solution? 500. The milliliters would get a 1. So I just took the concentration and I use it almost like a unit conversion. So it would be 500 micrograms per mil, but I could also say 1 mil per 500 micrograms. I could flip that, setting it up, because then it's going to show you that micrograms and micrograms will cancel. Does that make sense? So this is what I'm using, okay? So see, so if you have a solution and there's 500 micrograms per milliliter, so this is 500 micrograms per 1 milliliter. So do you see that I could flip it and it would be saying the exact same thing, 1 milliliter over 500 micrograms. So you could flip it, that's what I'm using down here. So I'm multiplying the amount, so the mass of the medication. I'm going to then be dividing it by that concentration. So 250 divided by 500, 0.5. Yep, so volume you know is going to be in liters, so that would be 0.5 milliliters. So the first answer was just the unit conversion I had to do. I couldn't do this last step unless they were both in the same mass unit, right? Because I started off with milligram and microgram. I got to put them both in the same unit. Now I can set it up so that those units will cancel.
And is that when did you do like multiply the 250 divided by 500? Is that how you got?
Yes, so if I do this math, 250 times 1 doesn't change, divided by 500.
And then
that gives you the 0.5, so 0.5. Okay, so you will see this kind of like over and over and over, and you'll have to do like how much medicine do you give per body weight, how much medicine in a solution. If you have to give medication as an IV, you have to do drip rates. So all of those, you will see that those come into play, but always make sure that you check those units. Because if you're given a value and it's in grams and you need it in milligrams, you're going to have to do a unit conversion to make sure that you get straight. Okay, so then we went on and we were talking about significant figures. So in significant figures, and if you were in lab, if you took the Chem 130A lab, we did a lot of significant figures, rounding, and unit conversions in lab yesterday. So hopefully this is now just kind of like updating. If you didn't have to take the lab, it's not a problem because it's still the same information. But the key things to remember is that all numbers between 1 and 9 in a measured value are all considered significant. It's only the zeros that you have to ask yourself about. So remember that zeros are significant if they're in between non-zero numbers. And zeros are always significant if they're at the end of a number and there's a decimal place anywhere in the number. So it doesn't matter, the decimal place could be up front, the decimal place could be in the middle, the decimal place could be at the very end. If you see any decimal place, all zeros at the end of the number are significant. So those were kind of my two examples. So that 10,001, those zeros are in between. So this would be 5 significant figures in the number. 120.00, because there's a decimal place, all those zeros at the end now become significant. So there's all 5 of them. The zeros that don't matter, the zeros that don't carry this measured value, are zeros out front, like 0.001. Zeros out front, even though there's a decimal place, the ones out front don't count. And zeros at the end if there's no decimal. And that is because with the number 1200, you know the 1 and the 2, but those zeros are not measured values. So the 1 and the 2 are what you measured. Those zeros are just telling you how big the number is. So the easiest thing to do with these is really to just try and do some practicing with them. Okay? And then we can practice rounding too. So like remembering how to round significant figures can be a challenge as well. So in this first one, how many significant figures in this number? 6, exactly, all of these. Okay, so the 0 out front, never significant, but the 0 in between is, and then all the non-zero numbers are. So there was 6. What about the second one? 3, because there's no decimal. If there's no decimal, zeros at the end don't count. What about the next one? All 8 of them. The zeros in between are significant regardless of the decimal place. If they're in between, they're always significant. What about the next one? 5. So remember, it's just the non-zero numbers. Zeros out front, not significant. So what about this one? 5 as well, okay? And it's these. The 4, 5, 1, which no, but then those zeros at the end are significant because there's a decimal place. The ones out front don't count. Those ones they're never significant. What about this one? 7. Yeah, there's 7. So there's 7 in this one because there's a decimal place. That decimal place tells you that you measured exactly to the million. So like I measured exactly 1,000,000 pennies. Counted every single one of them. So that means that all those zeros are part of the measured value. Whereas if I just put 1,000,000, then it would be what? It would just be 1. So if I just had this, 1, 2, 3, 4, 5, 6. Sorry, 1 too many. So if I just had that, that would only be 1, right? There'd only be 1 significant figure, just the 1, because it's just 1,000,000. So that means like, I know the 1, but the rest of them, it might be a little more or a little less, and so those are not measured. Whereas this one, with 1, 2, 3, 4, 5, 6, 7, all 7 of them are. Last one. All of them. The zeros in between are insignificant, but because there's a decimal place, the 0 at the end is. So that's 7. So now let's practice a little bit of rounding. So in rounding, you go from the left, find your first, count the number of significant figures that you want, and we're just going to do, for an example, we're just going to round to 3. Okay, sometimes you'll round to 2, sometimes you might round to 4, but whichever one it is, you just start from the left, find the first significant figures from the left, or the largest significant figures, and then from there, it won't let me change color, and then from there, you've got to round the next digit. Okay, so for this first one, 3 significant figures, I start from the left. Do you see that the 1, 2, and the 0, those are the first 3 significant figures, are the largest ones. So I'm going to have to round there. So the next number is a 5. So what is that going to do? It's going to round up. Anything up 5 or greater rounds up. Anything below 5 would round down. So this, I keep the 0 because I have to have that 0 out front to show where the decimal place is. I have to keep the decimal place. And I'm going to put 1, 2, 1. So that 0 rounds up to a 1. That's 3 significant figures. I do keep the 0 out front because it shows you where the decimal place is. What about the next one? Okay. So, do I need those last 2 zeros? Yeah, because think of it this way. When you round, you've got to keep the same size of the number. Do you see that 12,500 and 125 are not the same amount? Okay, so I need the zeros at the end. Does that mean these zeros are significant? No, they're not significant, but they're there to show the size of the number. What about the next one? So starting from the left, what's the first three? 4, 5, 6. Next number's a 1, so what happens to it? It'll round down, right? So remember, so I would keep these 3. The next is a 1, so it rounds down. So what becomes that? What does that 1 become? It becomes a 0, right? So 4, 5, 6. I have to keep a 0. So you see that 4,561.0025 rounded to 4,560. The number is very similar in size. So I still need that 0 because that tells me how big the number is. Okay, what about the next one? 258, 259. Is that it? You need your zeros in the front. So do you see, that goes from being a really small number to being 259 if I don't have the decimal and the zeros. So I keep the zeros and the decimal out front to show the size of the number. How about the next one? Okay, so the first three you find is 451. The next is a 0, so those do what? They just round off. But I still keep 00451. I would still keep the zeros out front just to show the size of that decimal. This, because it's the way that it is, do you remember you had to put a line over the top of zeros that were significant? I'm not going to ask you that on an exam, but that's what I would have to do. It's kind of a pain. 1, 2, 3, 1, 2, 3. I'd have to do it like that. That would tell you the 1 is significant and so are those 2 zeros. I'm not going to ask you that on an exam. I just ask it for the significant figure effect. And the same thing, this one, what would you have to do? 9,500.120. Yeah, so it would end up being 9,500. And in fact, that 0 would end up with a line. These, I will tell you, can sometimes be important when you're doing rounding with calculations. So you may have to go back to a measure number and check to make sure your final answer has the right number of significant figures. You will see this a lot more in lab, but covering these will really make a difference. So significant figures, really, now you're going to do this. Significant figures really come into play. It's going to kick me off, watch. Yeah. Oh, good, it did. Then we'll go back. Sweet. Score 1 for me. See, now I can use those little things. They really become important when you have to do calculations. So that's really like just understanding significant figures and doing this rounding. You're sort of like, what's the point of this? Well, the point really is because we use it in math. We use it in the calculations. You use significant figures whenever you do multiplication and division. When you do multiplication and division, you're always going to do the math. But then a lot of times, you know, like a lot of times when you put numbers in a calculator, you end up with 10 numbers, and you're like, I'll just take these 2. That's what I see students going like, well, I'll just say that's 3.5, even though it was 3.487964 all the way across on the screen. And so this actually tells you how to round. This is the rule. Whenever you do multiplication and division, your final answer should have or be rounded to the least number of significant figures in the problem. Okay, so multiplication and division, you need to know how many significant figures in the measured numbers. Addition and subtraction, they don't care. Addition and subtraction, you round to the smallest decimal place all the numbers have in common. So they work different. Addition and subtraction, you just round to the smallest decimal place all those numbers have in common. And sometimes it might be the ones place. Like sometimes, like you might not even have a decimal, so you just round to the nearest whole number there. But maybe they share the tenths. Maybe you add 3 numbers and they all have, one of them at the smallest decimal is a tenth, so then you would round there. So the easiest way to do this is just to do some practicing. So first off, just to make sure that you've got these, you tell me how many significant figures in each of these numbers. So 0.120. And if you don't know why it's got the number, just throw your hand up so that we can talk about it, just to make sure. So remember, it's the 1, 2, and the 0. What about 2.782? All of them. What about 12,500? 3. Just these, because remember, zeros at the end are not significant without a decimal. What about 3.7? 2. Okay. 456.025? 6. 200 or 2.30? 3. Right? 0 at the end is significant because there's a decimal. 19.2544? 6. All of them. Those ones you never miss. 25.896? 5. 15.7896? 6. All right, what about this one? 0.004510. 5, right? So it's these. And then 0.0256, 3. A million with the decimal place, 7. And then 12.56, 4. 9,500.120, 7. 3.6, and then 152.1, 4. Good. Everybody feel, all right, that's not too bad. Just identifying significant figures. We're not actually going to use them with the addition and subtraction, but it's just a good thing to practice. So now I want you to do the math. So get your calculator, do the math for the first one, and tell me all of the digits. Do them to check. 0.12 times 2. Yes, 0.33384. Got 84? 84? Okay. Okay, so how many significant figures in that answer? How many are there now? 5, right? So the 33384, 0 out front is not significant. So there's 5. Can it have 5? No, it can only have 3. So the rule with multiplication and division, I've got to round it to the smallest number of significant figures in my problem. So I got to round this to 3. So in rounding it to 3, start just like we do with the rounding before. Just start from the left, underline or identify the first 3 significant figures you see. So the 333. So then that means the rest of this has to go. So what happens to my number? Yep, so 0.334. All right, do the next one. 12,500 divided by 3.7. Whew. Yep. Okay, and that's just what the 10 digits that show up on the calculator. So this is the one I tell you, like, students do this, and they're like, I'm just going to say that that's, like, they just, like, randomly pick. I'm just going to say, I'll round it at the ones, right? I'll just drop all the other ones off. But that's not actually true. So looking at it, how many significant figures in that number? 378.378,378. 10. Can't have 10. That's way too exact a number compared to the numbers in the problem. So I got to round this to 2 significant figures. So just like before, start from the left. The first 2 significant figures are that 3 and the 3. The next number is a 7, right? So what's that 7 going to do? Round it up. So my 3 becomes a 4. So do I leave it at 34? What do I have to add? Add 2 zeros. Okay, I don't put a decimal place, but I put those 2 zeros to show where the decimal place is and the size of that number. Okay, so now this. So with this, when you're doing addition and subtraction, do the math first. So you've got to go and add those numbers. Yep. 477.5794. Okay, everybody got that? Okay, so now with this, there is how many significant figures? There's 7 of them, okay? But you really don't care about that. So what you need to do, though, is you need to figure out, you look, what is the smallest decimal place all those numbers have? The tens, the hundred, or the thousand? Hundreds. So you see the middle number? So here I've got 2, here I've got 3, here I've got 4. So 2 is the smallest. So that tells me I have to round this to 2 decimal places. So when you add and subtract, you find the smallest decimal place, and it's going to round from there. So that's a 9. So what will it do? It's going to round it up, okay? So my number becomes 477.58. Okay, try the next one. So see this one? How many decimal places there? Okay, this one has 3, this one has 2, this one has 4, so I've got to round it to 2. So you just look at each of your numbers, whichever one has the smallest number of decimal places, that tells you how to round.
So that's only an addition?
Only an addition and subtraction. Okay. So significant figures really doesn't matter. With addition and subtraction, significant figures doesn't come into play. With addition and subtraction, it's the number of decimal places they all have in common. So try this one. So 25.896 minus 15.7896. You get 10.1064? Okay. All right. So then tell me how many decimal places do I round? 3. So you see this one has 3 decimal places. This one has 4. So I'm going to round it to 3. So you just find the 3 decimal places. Next number is a 4. So that does what? Drops off. All right. So it'd just be 10.106. The next one. It's another 10-digit number, right? Right? You got a whole lot of stuff. All right, so what do I have to round this to? I have to round it to 3. Okay, so see that I have 3 in the denominator, so I'm going to have to round my answer to 3. Starting from the left, do I underline the 0? No. Remember, 0 is out front. Don't count as significant. The first 3 significant figures is that 176. Next number's a 1, so what happens? All of those just round off, so 0.176. I keep the 0 out front because it's just showing where that decimal is located. It's not a significant figure. Bless you. 1,000,000 times 12.56. So what do? Right? How many significant figures in that number? 4. Okay. So I don't have to add a decimal place at the end or anything. I just leave it. Okay. So with commas in the appropriate 12,560,000.
This was like a test. Would you count off if we didn't put commas?
No. I don't care if you put commas. I just put commas in so I can tell what the number actually is, so that I don't say that it's like 1.2, 1 million. And so I'm look at it and go, oh, that's actually 12 million. Okay, so the last one. Don't round anything until you finish the math problem, okay? And that's one of the reasons in lab, like I was having you set up unit conversions and doing them like in one long thing. So we calculated, if you weren't in lab, we calculated we had to go from ounces, or we had to go from cups to gallons. We had to go from like using like English units where you were setting up like 6 unit conversions all in a row. One of the reasons you do it this way is so that you don't worry about like rounding inappropriately. If you don't round till you get done, then you round only one time. You always like round at the very end. And that can sometimes be a challenge if you try to like do this little math part, this little math part, this little math part. If you don't carry them along, they become a problem. So this is 9655.82. Everybody got that? 820. Anybody not get that? If I just added all of those? What do I have to do though? Okay, so see, this is 1 decimal, 3 decimals. I'm gonna round to 1 decimal. So you always just round to the number of decimal places they all have in common. So my 1 decimal is 8. So what happens to the 2 and the 0? They get dropped off. So 9655.8. Okay, so Sunday night, you have a unit conversion dynamic study module and a significant figure dynamic study module will do. So if these seem like, okay, I think I got this, okay, then go through and do those. So that'll help you to see, all right, I gotta practice this more. Or maybe it'll help like, oh, that's why. Like sometimes doing those, things kind of click as well. So make sure you get those ones done by Sunday night. So the last math part is really not I think it's the easiest part, but it's called scientific notation. And this is because you will see numbers that are extremely big, like the number of molecules in the mole, 6.02 times 10 to the 23rd, Mr. Avogadro's number. And so having the understanding about what this means, so that number, when you see that exponent to the 23rd, that means your decimal place would actually go 23 places to the right. So if I was going to write this out, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. So those are equal, okay? But trying to do math with huge numbers like that can be a challenge, which is why they went to scientific notation, putting things in an exponential form. So see the difference. So all I did was like, I would take this decimal place. If it's a positive exponent, the decimal place would move to the right by the number of zeros. So if you had this number and you wanted to put it in scientific notation, first off, you see you don't see a decimal place, so that means where is it? At the very end, okay? And if I want to make it and put it in scientific notation, I always put it so that my number is a number between 1 and 9. So I'm going to move that decimal place. I'm going to go to the left. How many places? I want to make my number, final number has to be between 1 and 9. So I've got to move it 9 places. So I'm going to take and move. It's here. 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm going to have to move it 9. I'm only going to list in scientific notation, I'm only going to list significant figures. So how many significant figures does this have? 5. So I'm going to have 1.2698. I leave those zeros at the end off because they don't have a decimal after them, so they're not significant. And then I say times 10 to the 9. So when a number is bigger than 1 and you change it to an exponent, it's always a positive exponent. But then we're also going to talk about numbers like this. Okay? Like this is like the size of the mass of an atom. Crazy, stupid, small, right? But you don't want to have to sit and write 0, 0, 0, because you know what will happen is you'll miss 1 0. So you don't want to have to like take notes and write all these zeros in all the time. So instead, they just describe them according to scientific notation. So you tell me, count that one. I'm going to start where the decimal is, and I have to move it to the right in this case, so my number becomes between 1 and 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So this would be 1 times 10 to the negative 17 grams. Okay? And notice I just put a 1. You don't have to put 1.0. I just put a 1 because the 1 is the only significant figure in that number. I had to go 17 times to get my decimal place behind that 1.
So you did 21 zeros at the top. So the 02 would make it 23, correct?
Correct, because I would start at behind the 6 is my decimal place. So I'd actually start just making, I do them like little loops. I just kind of go along and count them that way. So I would end up doing 23 little U's and then add 21 zeros because the other 2 are where the 02 was. Okay, same thing here. If I started over where this decimal, I'd count as I went, keep going and counting until I got my decimal place all the way to here. And if you count those many, that would be 17 places. So it's 1 times 10 to the minus 17th. Okay, so put these ones in scientific notation and make sure you keep significant figures. And then if you get down to the bottom ones, then you put them back in expanded form like standard writing. All right, so let's work through some of these. What did you get for the first one? How many significant figures, first off? 6. So everybody sees these are the 6 significant figures I'm keeping. So I'm going to drop those zeros off at the end. So I've got to start from the end. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 1.20568 times 10 to the 9th, right? It's a positive number because my number is bigger than 1. 12,500. What'd you get? Times 10 to the 4th. Okay. Sometimes doing exponents doesn't really help because how many significant figures in this number? Nope. How many significant figures in this number? All of them. Right? So 400. Oh, I thought you might have been talking about 12,500. I was talking about the next one. Okay. In this one, sorry. Okay, so 456.00025, all those are significant figures, so I can't drop any of them. So sometimes going into exponents, it doesn't really help your number. The top one, I think it makes it a little easier in terms of like writing some of these ones down towards the bottom with really lots and lots of zeros really makes a difference. But if I was going to do this, I would just move this 2. So it would be 4.56, but I'd still have 00025 times 10 to the 2nd, okay? So it almost seems like more work to put it in exponents, okay? So just know that it doesn't always, but some ones where it's a really small number, which way does that decimal go? To the right, to the other left, okay? To the right, so it's gonna go 3 places to the right. So this would be 2.5896 times 10 to the negative 3. So remember that if the number is smaller than 1, it's a negative exponent. So if you see an exponent with a negative, just always make sure that you go to the left when you go back to expand it. So what about this one? 4.51. 00, right? Because remember, these are significant. The zeros at the end, if there's a decimal, any zeros at the end are significant, so I got to keep those. This would be then times 10 to the negative 6. Good. This one just looks like those zeros all like run together when I start trying to count them. So that's why I always do because there's a lot of zeros. It's easier to just go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay? So that way you can like make sure that you don't double count zeros. So this would just be 1 times 10 to the 14th. Now, how would you go if you're going to put this one back into normal form or standard form? Which direction would your decimal go? To the right. How many? 6 places. So at the end of this, I would have 2 zeros. So it'd be 9, 5, 1, 2, 3, and 2 zeros at the end. How many places would I go this one? So how many zeros at the end? 9. 1, 1, 2, 3, and then 1, 2, 3, 4, 5, 6, 7, 8, 9. And then this last one. So which way does this decimal go? Left. How many? 6. So you'd have 0 point, how many zeros now? 5. 1, 2, 3, 4, 5. 9, 5, 1, 2. Oop, there's a 2 in there. 9, 5, 2, 1, 2, 3. Keep all of those, wouldn't round any of them, but my number, because it's a negative exponent, the number would go that direction, to the right, to the left. Okay, so I really don't think it's just a matter of remembering. Just remember, if your exponent is positive, you know that your number is bigger than 1. If your exponent is negative, your number is smaller than 1. So moving your decimal place appropriately so you don't mix those. So 2 applications of some of this math. One is percent, and most everybody knows what percent means, right? So if you get a grade, if you get an 87 on a test, you know that means 87 out of 100. So percent is always out of 100, and it really puts things on a good scale. So if there was 500 things that you were trying to collect, or there was only 50 things you were trying to collect, so putting it on a percent allows you to figure out, okay, this is like, what percentage do I have out of all the ones I want? So it is always defined as being whatever part divided by the total number multiplied times 100. Because part divided by whole, so if you get an 87 out of 100, if you divided that, you get 0.87. So multiplying it by 100 puts your percent on a scale of 0 to 100. So then you're like, okay, I fall into that 87 range. So it gives you an idea, and I'll tell you, like, I always have mine sort of figured out, so my points and everything end up being 100% total. But I worked with a guy in Wilson, and he used to write exams that would just, like, sometimes they were 400-point tests, sometimes they were 300-point tests, sometimes there were 700-point tests. And so you would get a grade back, and so it might be that you got 625 out of 800 points. And so people will be like, well, what does that mean? Okay, so being able to then, so if you got 625 points right out of 800, that's the part is 625, 800 would be the whole. So to get this into percent, you would just divide, You would just divide these two and multiply your answer times 100. And that way, you could give yourself a percentage, huh? There's a frog over there. All right, so you just take 625 divided by 800 and multiply that answer times 100. So then it comes out as 78.125%. Now, if I was going to do that, and I had to round this, what would you round this to? Thinking about significant figures. What would you? 78.1. So this is, right, so this is your score. And this is like the max, right? So that's like the maximum you could have gotten the whole. So that's really an exact number. 800 is the exact number. I scored 625, so I'd say, okay, I got 78.1. I'd round it to 3 significant figures based on that top number, because that's my measured number, how I did in comparison. So let's do a few. So here's a question with just coins, just basic questions, and then the other one is looking at baby weights. So the first one, you have 48 coins, 12 are quarters, 20 are nickels, 10 are dimes, the rest are pennies. Determine the percent of each coin. So how do I figure out the quarters? So it'd be 12 divided by the total, right? So 12 are quarters divided by the total, which are 40 total. And then my answer times 100. Okay? And that comes out 25%. All right, now I got the next one, so 20 are nickels. So 20 out of 48 of them are nickels. And then multiply that answer times 100. And you get that. How do you round that? 42%. So you'd round, so 20, that measured number. 42%. 10 are dimes. Multiply that answer times 100. So first do the division, then multiply, because you'll get like a fraction or a decimal place, multiply that answer times 100. So this one is 20.83333333. And that one you'd round, 21. And then the rest are pennies. So what's one way you could figure that out? Okay, so if I know 25, 42, and 21, the rest are pennies. So if I took 100% and I subtracted 25, and then I subtracted 42, and then I subtracted 21. Subtract, 12? To get to figure out the rest of them. You could also subtract the number of coins that you know, 48 minus 12 minus 20 minus 10. And that would tell you the number of pennies, and then divide that by 48. Either one you could do. Because the total, whenever you use percent, the total amount is always going to be 100. So 2 infants in PICU, which is the perinatal ICU, so they're usually preemies or have some kind of issue. 1 infant's weight increased from 126 ounces to 147 ounces. The other infant's weight increased from 86 ounces to 103. So when you first look at this, who do you think gained more weight? Just eyeballing it. What do you think? Okay, so people like go, oh, the first one's bigger, right? So they're bigger to begin with, so they gain more weight. So which infant had the greatest percent weight increase? So if I'm looking for a percent weight increase, what do I have to do? So first I need the difference, right? So I have to subtract. So I have to subtract their final weight minus their initial weight. And that's going to tell me the change. Now that's just telling me the change. So like for infant 1, I'd take 147 minus 126. And so that's what, 21? So it's 21 ounces. But to figure out percent, I'm looking at the total. So what would I use? So that's the change compared to, would I use the 126 or the 147? So that's their final. So that's like really what I use to figure out the change. But they started off at 126. So that's their initial. So their percent change looks like compared to what they started at. So I would then take 21 ounces divided by 126. That's going to give me a fraction times 100, puts it in a percent. Okay? Yeah. So it would be rounded to 17 because of the first change of 21. So I'd round that to 17%. So now do baby 2. So when I subtracted to find their difference, how much weight change did they have? Only 17 ounces. But how is this different? When I divide it, what do I divide by? The 86, because that's where their starting point was. So now I get a decimal, multiply it times 100. That's 19.7674419. And if I was looking for 17 is 2 significant figures, so I would round that one to 20. So in fact, baby 2 gained more weight because they started off at a smaller weight to begin with. Okay? Gained more percentage-wise. So it does sometimes depend on like the amount of your whole. Like how big is your whole number compared to the part number that you end up dividing it by. Now we'll go on to that. right? So the last part, so this will probably be the last, we're like 90% through this chapter. So the other kind of application in the math is talking about what's known as density. Okay, we've talked about mass, we've talked about volume. So you remember that mass is a measure of the amount of material that a substance has, right? So it's how much a substance has. And we use the gram. You could have milligrams when you're talking about things that are really small amounts, like a tablet of Tylenol, or you might be talking about kilograms when you're talking about something that has a large amount, which is more like body weight, 2.2 pounds. You can think of it as being equivalent to weight, but in fact, weight is really relative to the pull on mass by gravity. So it's really the only way that we are able to measure things. So we use the balance in lab to measure things in mass. But like if you were in space, you wouldn't have the same weight, but you would still have the same mass. So your atoms, your particles that make you up would still have the same components. So that's kind of the difference. But everybody just thinks about weight and mass as being pretty much the same. And on Earth, yeah, pretty much. Okay. Volume, though, volume is this three-dimensional idea. So volume is the amount of space that matter takes up. Volume varies as well. Remember, you could have something really small, like a milliliter. So that may be like if you're giving an injection, it would be in milliliters. But it could also be in liters, like my 1 liter bottle. Try to drink those every day. It can also be really large volumes like kiloliters. So there's variations in volume just by changing the unit size. Just one note that's kind of interesting that sometimes people know, sometimes people don't know, that there are equivalents of milliliter, 1 milliliter, is equal to 1 cubic centimeter. So a cubic centimeter would be like a little cube that is 1 centimeter tall, 1 centimeter wide, and 1 centimeter deep. Okay? So think of it if you had an exact little block. If each side was exactly 1 centimeter, then remember to figure out volume. You would do length times width times height. So 1 cubic centimeter is the equivalent to 1 millimeter, or milliliter, milliliter. So they'll sometimes call that cubic centimeter a cc. So you might see on a syringe a 3 cc, a 5 cc syringe. Just keep in mind, cc and milliliter are equal. They're interchangeable. So if you see a 3 cc syringe, and then you see a 3 ml syringe, don't be like, I don't know what this one is. They're saying the exact same. It's just sometimes they use one more in a solid volume measurement. The other one they use as a liquid volume measurement. So just know those are the same. So density. We can have varied mass. We can have varied volumes of any kind of substance. But the amount of space a substance takes up and how much substance it has in that space is actually consistent. So density is something that can be described according to all the elements. You can describe the density of any element. You can also describe the density of any pure compound. So if you had a sample of water and it was pure water, you could define the density by measuring its mass and the amount of space that it takes up. And so if I had like a 1 liter bottle of water, or if I had a 2 liter bottle of water, they would have the same density. It would be twice the volume, but it would have twice the mass. So my density calculations would be exactly the same. Just in comparison by, and of course they always had to say, all right, well, we've got to make some kind of consistent. We're going to make like a constant. So they came up with density and they said water is going to be our constant. And it was one of the things that helped develop the gram. Okay, the grams and volumes is they said 1 gram of water, this sample of water is going to weigh 1 gram, and it takes up 1 milliliter of space. And so therefore, its density is exactly 1. So this is kind of like the reference that everything is based on. It's really helped them to devise or develop the metric system. They were like, well, what are we going to call a gram? I don't know. So they came up with this. Let's call 1 gram this. Okay. And then everything else is going to be varied kind of based on this one set standard. 1 gram of water takes up 1 milliliter of space. So its density is exactly 1. So anything that is less dense, if it doesn't mix with water, it will float. Okay? So if you have like oil in water, or if you've ever seen like gasoline spilled like at the at the gas station, do you notice how it makes like this like rainbow color like on top of the water if there's a puddle or anything? That is because gasoline and those hydrocarbons are less dense. So that they don't mix with water, they separate out and they float on top. So like their example, a piece of wood, anything that floats, you know that the density has to be less than 1. Anything like a penny, you drop a penny in a fountain, drops to the bottom. So anything that doesn't float, that sinks, you know it's going to be more dense than 1. So you could really kind of define things as being more or less dense based on this known sample. But we can also do the calculations. So if we know that density is equal to mass divided by volume. So D equals M over V. So if I know the mass and I know the volume, I can figure out density. But if I know the density and I know the volume, I can figure out mass. I will always give you like 2 out of 3 of these values, and you may have to rearrange the formula to figure out the other one. But you will always have all but one of the numbers. So here's this one. So this one says a 1 liter volume of sugar has a density of 1.29 grams per mil. Determine the mass of the sugar in the sample. Okay, so remember how we were doing this in class, and I said, okay, when you get in lab, remember when you get a word problem, like everybody goes, oh my God, I can't do it, okay? So first thing you do is you read the sentence and you ask yourself, okay, what do I know? Okay, you know the density, okay? So pick those things out. Here's what I know. Sometimes it's helpful if you just underline, because we're going to take it out of a sentence, so we're just going to make it a math problem, and then it's not a big deal, okay? So I know that the density of this sugar is equal to 1.29 grams per milliliter, right? So if you see grams per mil, that's really what it means, is grams divided by 1 milliliter. So that's the unit, is grams per mil. What else do I know? I know 1 liter, and that is what? Volume. So I also know this. So I also know volume. And it's 1.00 liters. So now I want to find that. I heard it. Say it a little louder. Mass. So what I want to find is I want to find mass. Okay, so now I know. So if I know density, I know this, right? And I know volume, so I know this. This is what I don't know, right? I don't know mass. So I need to have mass all by itself in this formula. So you can simplify the formula and just say D equals M over V. Density equals mass over volume. Just so that you have letters to move around. It's easier than moving around words. So the one I got to get all by itself is M. How do I do that? So remember in algebra, what do? Multiply both sides by V. If I multiply both sides, remember in algebra, you can multiply both sides by the same thing. It doesn't change any of the other values. But what does it do to my right side? It gets rid of volume. So do you see that V and V will now cancel? Something's in the numerator and the denominator. So volume and volume cancel. So now I actually have my formula. Now I know that I just take the mass, multiply the density times the volume to figure out my answer. Density times volume will tell me mass. Okay? So what's the other thing I have to do, though? Anybody see it? I have to do a unit conversion. Why? Which ones? So grams, I only have 1 gram measurement in there, but what's not matching? Right? Do you see that I have milliliters and liters? Right? So if I just multiplied the density of 1.29 grams per 1 mil times 1.00 liters, do you see that they won't cancel? Okay? So I've got to convert one of them. You could convert milliliters or liters. It doesn't matter, but you got to put both of those volume units the same. I would change liters because it's all by itself. So I just find it's always easier to do a unit conversion on something all by itself, like it doesn't have another unit value to it. So I need to know, what is this in milliliters? That's just a single unit conversion, so do that. So what unit did you put on the bottom? Milliliters on the top. Milli gets a 1,000. Liters gets the 1. Right, so that's going to get rid of liters. Put my answer in milliliters. So this is 1,000. So now I can substitute this in. So 1.29 grams per 1 ml times 1,000 milliliters. Do you see now milliliters and milliliters will cancel? And it's going to leave me with my answer in grams, and that's my mass. So this would be what?
1,290.
Okay. So now always last step, go back up. How many significant figures in 1.00 liters? 3. Okay. Density, it only has 3 significant figures, but density is like a known number. It's not a measured value. The only measured value in my problem is that 1.00. Because this would be considered like a reference value. Density comes from a table, so I would look it up in a book. And so anytime you have that, it's not measured, so I wouldn't use that in determining how to round. So I would use just the 1.00. So do I have to round this? No, it's good, okay? 3 significant figures, so I don't have to do anything to it. 12,900, okay? Anybody have a question on that? Everybody understand? I saw some question looks. I saw some faces like, All right, let's try one more. Go to the next slide. Yes, sir. Okay, now I'll go 5 times. A tablet of Tylenol weighs 678 milligrams and it has a volume of 0.17 mils. Determine the density with the correct significant figures in grams per mil. Okay, so first do the exact same thing. Underline, what do I know? What do I want to find? Rearrange the formula. Make sure your units match. Then do the math. So if you're going back and you're trying to like study and practice in this and you were like, she wrote some steps on that PowerPoint. I actually saved these PowerPoints. They are posted in Moodle. So this is posted as Chem 130 Chapter 1 marked up PowerPoint. So all of the notes that I add to things, and even if I add another page that maybe you don't have on your PowerPoint, those are all there. So it's always an option. It's always in the module that matches its exam. So right now I'm just posting things in the Exam 1 module. Also remember, if you ever miss a class or if you want to go back and listen to a class, I record these lectures. I do try to pause, like when there's long periods of time that you're working on stuff. And if I'm like calling roll, I do try to pause so that I'm not calling everybody's name while recording. But those are all posted on YouTube, and you can like jump forward to a specific area if you just wanted to rewatch it, just as a reminder. All right, let's see if we can finish this one. So what do I know? I know mass, okay? So I know mass, and you can do it as simply as just underlining and writing what it is, or you can make the list as you go. Okay, what else do I know? I know the volume. So what do I want to know? This is what I got to find. Okay, I got to find density. So here's my formula. So remember it was D equals M over V. Density equals mass divided by volume. Do I have to rearrange this? No, it's exactly the way it is, okay? So do the units match. So in this one, I want to find density, and what is it, the units that density needs to have? I need my units to be grams divided by mils. So is that the case? Is my mass in grams? No. Is my volume in milliliters? Yes, so I'm good with the volume, but I need to convert the mass. Okay, so 678 milligrams. I need to convert it to grams because it asks for my answer in grams per mil. So 678 mg times in a line. What goes on the bottom? Milligrams, grams on top. This is single step because I have grams. Milli gets the 1,000, grams gets the 1. So this is 0.678 grams. So now I've got grams and I've got mils. So now I do step 5. I just do the math. 0.678 grams divided by 0.17 ml. What'd you get? Yeah, so this one's a good one. So 3.988235294 grams per mil. Right? So you get like 10 digits. So then the last question you got to do is I've got to apply significant figures. So are those measured values, mass and volume? Did you measure those? Yes. Okay, so I'm going to use both of those. So I wouldn't use density because it's a reference number or a standard number. But those, a tablet weighs, so I know those are measured numbers. So 678 has 3. 0.17, 2. So that means I'm going to round to 2. So if I look back here, starting from the left, just like before, starting from the biggest significant figures, the 3.9, so that means all that other stuff, what happens? This is an 8, so what will it do? So it's going to round the 9 to a 10 and the 3 to a 4. So I would end up rounding to 4.0, keeping 2 significant figures in that answer. Okay, so not terrible. So the only part that we have left to do in this chapter is we really just have to talk about a couple of other things. So there's really no more math. It's really just like, okay, well, what is specific gravity and its relationship to density? I want to talk a little bit about temperature, just because you'll be using thermometers. We will talk about temperature, kind of doing like Celsius versus Fahrenheit, and then mentioning Kelvin that we will use later on. And then finishing like why body temperature is the way it is. And then finishing up just with some of the measurement values that you'll see with energy. Because we will talk about that some in chapter 5. And that finishes up what they call specific heat. So there's really just kind of a little bit of theory things to finish in chapter 1. That should take us maybe 15, 20 minutes on Tuesday. Then we're going to start chapter 2. So I want you to make sure you get pre-lecture chapter 2 done by Tuesday. Okay? Make sure that you get the dynamic study modules for significant figures and unit conversion done by Sunday night. Okay?
What was the answer for the Tylenol question?
So 4.0.
Okay, just making sure I got it right.
Yeah, in the rounding, 4.0. Good? All right, please drop the calculators off on your way out.